Okay, thank you everyone, and thank you Ed for the wonderful opening. I think Ed just showed some magical demos to show how one single database of TiDB can handle both traditional transactional workload and also the analytical workload at the same time, right? So now I'm going to talk about some hardcore part. Today, I'm going to talk about TiDB Optimizer behind the story just introduced by Ed. Optimizer can be one of the hardest part of the database kernel. I remember Professor David DeVee once described the optimizer as even harder than rocket science. So that explains how hard is the query optimizer. So today I will cover some basics of the TiDB query optimizer, and also I will talk about how we evolve our TiDB query optimizer to HTAP optimizer. So this is the agenda of today. First, I will talk about the TiDB optimizer, how we evolve the TiDB optimizer from handle OLTP workload to handle the HTAP workload. And then I will talk about some tuning practice, because we know there can always be a problem with query plan and the performance issue, right? So at TiDB, with TiDB, we do provide some tuning tools and tuning practice. So I also want to talk a little bit about that part. And then I will talk about the lessons we learned during the previous journey when we build up this TiDB and TiDB optimizer. And also, I will share some challenges we have faced and how we can overcome those challenges. And then at last, I will share some of our vision or some new features on the road we are going to deliver. Okay, so this is the general system architecture of TiDB. As you can see, we have three major components. The first one is a TiDB server. The second one is a storage cluster. And then we have another placement driver component. So that's the three major components of the TiDB. That's also the database behind the OSS inside demo Ed just showed. So in this single database, we have a TiDB server cluster, which handles the connection from the client. And we also do the query optimization and some query execution on the TiDB server side. And then in the TiDB cluster, we have, as Ted mentioned, we have both TiKV, which is a row store, and we also have a TiFlash, which is a column store. So both column store and row store are in the TiDB storage cluster. So we can handle both the OLTP and OLAP workload at the same time. And then we also have this PD cluster. The PD cluster is responsible for the data placement and also the timestamp. So this is the general architecture. And so you can see that inside one cluster of the TiDB, we do provide a capability to handle both row store, column store, and at the same time. And then next, I would like to talk about optimizer. So this is a simplified or classical optimizer on a textbook or on a paper. So in general, I think the nature of query optimization is a search problem. So when given maybe a very huge search space, and optimizer need to find the optimal plan inside this search space. So that's basically is a search problem. And it's proof that it's an NP hard problem. It's really hard, which means you probably cannot find an optimal solution within the polynomial time. So this is really hard. And then there are several components of this query optimizer. We have this search space. And another thing is that we do need to enumerate the different plan options and to enlarge the search space so that we don't miss the optimal solution, optimal plan in the search space. So that's very important. To do that, we have both transform or implementation. for the transform means that given a query, we have several rules to rewrite the query or do some kind of query transformation. So each of these rewritten query are just equivalent in the query semantics. And then we have an implementation. So implementation is in charge for the actual execution algorithm for each operator. For example, we have a join, right? Then for the implementation, we can select from next loop join, hash join, or somewhere join. So that part is done by implementation. And then, so we have the enumeration algorithm, we have the search space, and we do need a search algorithm. So search algorithm is very important because this is an NP-hard problem. So we need a very efficient search algorithm to find optimal plan. So that's important. And I think for the search algorithm, there are a very popular one. For example, the system R has this bottom-up dynamic programming search algorithm. And for the newer optimizer like CalSite or OCA, they use the cascade top-down search algorithm. So those are very important algorithm to search for the optimal. But for the search, but to get the optimal plan, we need to know what's the best plan. So how do we know? So that comes with the cost estimation. So with the cost estimation, we calculate the cost for each plan option. And then we compare all the plan options in the search space and then find the optimal one. So that's the cost estimation does. And so this, I think, is just a very high level and general idea about the optimizer. So basically, it's a search problem. It has a very huge search space, and the optimizer has to have an efficient search algorithm to find the optimal plan, which usually has the minimum cost. So that's the a typical or simplified optimizer. And then let's come to a TiDB optimizer. So this is a SQL layer. As you can see, the TiDB SQL server receives the SQL from the client and then pass the SQL and generate the AST tree. And then AST tree just you can see this as an intermediate data structure to transform the query text into a certain tree like the data structure. And then we have a validator to validate whether all the objects in the query are valid. For example, if do we miss any table schema, or if the column is not defined, all those things are done by the validator. And if we validate the query is okay, then the ST tree will pass to the logical optimization phase. At this stage, TiDB Optimizer will do the query rewrite and some of query transformation. And then the logical plan is generated. And then the logical plan will pass to the physical optimization stage. At that stage, we will choose the efficient implementation for each operator. For example, the join. We need to find the best join method for the join node. And also at the physical optimization stage, we do the cost calculation for each plan options. And then we find the best plan. And the best plan will be sent to the TiDB executor to execute. Here, you may notice that besides those general flow, we do have a statistics and a plain cache, SPM, and diagnosis component in the SQL layer. Those are very important part. I will talk about that later. And then you may also notice that the TiDB query executor will assign the plan, the subplan to the TiDB store engine. So that part is very important because we push down certain commutation to the store engine, to the storage engine. For example, we have a TiKV for the row store, right? And we have the TiKV coprocessor to handle like a filtering, some aggregation and the limit and top end, certain things, certain commutation. And also we have a TiFlash, and we have a TiFlash coprocessor too But TiFlash coprocessor is distributed. It's an MPP styled coprocessor. So you probably heard about the MPP. So which means that the TiFlash coprocessor can cooperate each other. They can shuffle the data and they can do the distributed join, distributed aggregation at the same time. So the optimizer needs to know which part of the computation to send to the TiKV, which part of execution need to send the TiFlash.
Yeah, and I will also want to point out this point is a very big differentiator between the traditional database and the distributed system. So inside TiDB, just like the demo I'm showing, we can see a lot of like the operator is COP, coprocessor. That means the compute is pushed down to the different storage node to do the distributed computing. So that's the one very big differentiator between the single node database and the distributed database. Yeah.
Yes, and then let's continue. Okay, now let's look at the inside of the query optimizer. So I already talked about the general flow of the query optimization. So the first thing I want to talk is the statistic. Why I want to talk this first? Because this is really important. The statistic really matters because for the optimizer, there are always some assumptions to do some query optimization. For example, the optimizer will always assume the uniformly distributed data, which means that there's no skew. That's the first assumption optimizer usually hold. The second assumption is that it assumes there's no correlation among the columns or among the different the tables. So that's second assumption. The third assumption always assume the inclusion, which means a PK, FK relationship when the two table, two column join together. But we all know that it not always hold, right? Those assumptions. In the reality, in the real world, we can see the data skew. We can see the correlation, strong correlation among the columns, right? So that means the assumption is broken. So optimizer can make wrong assumption and can make wrong decision. So that's a very critical issue. And second thing is that the optimizer, the stats actually is the source of truth for optimizer to find actually to do the optimization, to do the costing, and to find the optimal plan. So that's another thing. So if that's why I always say the garbage in, garbage out, which means if your stats is not good, how could you expect optimizer can generate a good plan for you, right? So that's why I always talk about the stats at the beginning. So this is really, really important to the query optimizer. So at TiDB, we do collect several types of stat, the table stat, the column stat, and the index stat. I won't go into the detail of each of the stats used. But you can always use this show command to find the stats used by the TiDB. And also for TiDB, we provide both manual collection of the stats and also the auto collection of the stats. So that's also important because if you just do the manual collection, that means after a certain time, you have the data change, right? So your stats can be out of date. Then the optimizer may use the stale or wrong stats to make decisions. So that can be dangerous. That's why we also make this auto or incremental statistic collection. But at the same time, we know that stats collection can be very time consuming. So for example, if you have 20 billion rows of table, and also the table can have like several hundred columns, if you just want to collect the stats on such a big table, it can consume a very, very long time. So that's why we also did some improvement of the stats collection. For example, if a user specifies predicate column option in the analyze command, then we'll automatically check a workload to find what columns we need to collect stats instead of collecting everything. So that can save a huge amount of resources and time. So that's one important improvement we are doing. And also, as I mentioned, as time being goes on, the stats can out of date. So for user, how do user know that the stats is out of date? So we provide this show stats healthy command to show whether your stats is out of date. So we can always check that to find if it's about 90% health code, then probably you're good. And then if it's lower to like a 30 or 20% of health code, health score, then your stats are out of date. You need to either manually run the analyze to collect the stats or kick in the auto collection. Okay, then next is the cost estimation. Actually, this part contains two major components or major parts. The first one is a cardinality estimation. The second one is the cost estimation. You can think the cardinality estimation is fundamental because it's the input to the cost estimation, which means for the cardinality estimation, we usually estimate the selectivity or filter factor of a predicate, either local predicate or joint predicate. That means we need to find out how selective of a certain predicate is. For example, this table has 1 million rows, and after this filtering, after this predicate, we need to find out how many rows survive. So that's the selectivity estimation. That part is very critical to the optimizer. And then we have the derived stats. Derived stat means after each operator, for example, after the join or after the filtering, your stats need to be updated too. So that's another part. And then for the cost, we do have our cost model. Here I want to mention that the cost model is very critical too, especially for the HTAP, HTAP system, because we need to differentiate the TiKV and the TiFlash plan. And because if you access the TiKV or you access the TiFlash, the cost can be different. Now, how could you differentiate the cost? The cost model kicks in. The cost model plays a very big role here. And then we do the cost estimation for each operators. For example, for the scan, for the join, and for the aggregation. And then we calculate the total cost for each plan option, for each possible plan. And then we find the minimum plan to be delivered to the per executor as the optimal one. So, but I think among these two, the cardinality estimation is more important. Why? Because it's the input to the cost estimation. So if the cardinality estimation is good, then very likely you can get a not bad plan. So that's also true. But if your cardinality estimation is a way off, then very likely you won't get a good plan. So that's why cardinality estimation is very important. And also we developed a framework to evaluate both the cardinality estimation and the cost estimation. So that part is to help us to find like a estimation bias and also help us to calibrate the cost model. And also I think one of the challenges for every optimizer is how to evaluate optimizer. I think the guy working with optimizer will always ask, how do you evaluate the optimizer? Is your optimizer good or not? And after certain version or certain release, how could you evaluate the improvement of your optimizer? Those questions are really challenging and hard to answer. So by developing this framework, we are going to provide a quantitative evaluation for the optimizer. So we can see, for example, how many % of the improvement for the cardinality estimation and by comparing to the actual selectivity, and how close your cost estimation to the actual cost. So that's the very important work that we have been doing. And then I think I talked about this logical optimization. Here I list some of the logical optimization done by TiDB. The first one is a query write. With the query write, we always like do the predicate simplification, join elimination, outer join to inner join transformation, and one of the important things is subquery decorrelation. Why subquery decorrelation is important for the distributed database? Because with the distributed database, you have to run the execution on different execution node. So without doing the decorrelation, it's really hard for the current execution model to handle the correlation execution model. So that's why we, for the distributed database, we always need to do this subquery correlation. So this is very important. And also, we also do the join reorder. So I think everyone probably know join reorder, right? So for example, we have a 3 table. Then how we join this 3 table? T1 join T2 join T3, or T2 join T3 join T1. All those there are a lot of combination, especially when the table, the number of table increase. This combination can be very, very huge. So we do have 2 algorithms currently. We do have a greedy algorithm to find the join order, and then we also have a dynamic program-based algorithm to find the good or optimal join order. And also we have some other logical optimization like column pruning, partition pruning, and also at logical optimization we also do the push down like predicate or limit or aggregation push down. And then after logical optimization, we send the logical plan to the physical optimization stage. At the physical optimization stage, there's several things. The first one, we need to decide what's the most efficient access path. For example, we may have the selection, or we may have a choice to use the index, and we may have the choice to use the table scan. And right, since we are HTAP, we also have a choice to use a column store. So we need to find which one is the best, which one is the most efficient way to do that. So that's an important thing. And the second one, at least the join method I already mentioned, we need to find what's the best join method for this particular join. Either hash join or index join or merge join. So, and also the aggregation, we have the hash aggregation, we have a streaming aggregation, or we can have other aggregation algorithm. So there are quite a lot of consideration or choices that we need to decide from. And after the physical optimization, we also do some extra optimization we call the post optimization. For example, we after certain optimization, there probably can can merge some operator together. For example, we may have a 2 filter node together, then we can merge this 2 filter node as one filter operation, something like that. Okay, so all the optimization I mentioned so far very common to OLTP or OLTP optimization, query optimization. But now, since we are talking about HTAP, HTAP, which means one single database handle both OLTP and OLAP workload at the same time together. So there are both pros and cons when we get to the HTAP. For example, since we handle both, since we do have the capability to handle OLAP and OLTP, which means we have more choices. And that's for optimizer is both good and challenging. Why? Because we have an even larger search space. Previously, you only need to search the options, for example, the index from the TiDB side or from columnar side, right? But now you have combined them together, which means your search space is enlarged. So that's a very challenging for the query optimizer. Be aware that the query optimizer already is an NP hard problem, so that makes it even harder. Although it's still NP hard, but it's even harder. So that's one thing. And also, since we need to handle both the OLTP and the OLAP workload at the same time together, which means for OLAP workload, there are always some very complicated or complex query optimization techniques. So that means that we need to incorporate those optimization into our TiDB optimizer. So that makes the query optimizer more complicated. And also we need to differentiate the choice between the TiKV and the TiFlash. So that's also a very challenge for the query optimizer. And there can be the query, since the search space is larger, so the overhead to do the query optimization can be high, the overhead. And so we need to solve those challenge too. And we need to mitigate the impact of the mission critical OLTP workload. Since right now we handle both TP and AP workload at the same time, we need to make sure the AP won't impact the mission critical TP workload. So that's also important. But there are also gains, actually tremendous gains for us, as Ed already showed you. So right now we can leverage the power of both TiKV and TiFlash, the row store and the column store at the same time. So that's one of the beauty of this HTAP system. Another thing is that since both AP and TP data in one database, which means there's no delay to do the OLAP workload analysis, because the data are all there all together. The TP data just come in, and we can at the same time we can do the analytical processing at the same time. So it's by nature it's just a real-time AP workload processing. So we can do that at the same time. So that's why I say no pain, no gain. But by overcoming all those challenges, we can get the power of this HTAP system. And here are some optimization we have been doing for the HTAP related query optimization. The first one is that we need to choose the storage, right? We need to have the ability to choose either from the column store or from the row store. And then we need to use our optimizer costing to differentiate the choice to find the best one. The second one is to XTAP selection. Whether we use the TiKV index or TiFlash column. And the third one, we need to define what we can push down to the storage engine. As I mentioned, we do have a coprocessor with both TiKV and a coprocessor with TiFlash. That means we can push down certain computation to the storage. So we can have the close or near storage computation. So that's also important. And then since our TiFlash processor is MPP, so we do have MPP related planning. Like for example, we can fragment the plan, subplan, and to send the plan to each of the MPP node to do the parallel distributed computing at the same time. So that's also very important HTAP optimization. So with all this HTAP related optimization, the TiDB query optimizer can efficiently choose the best plan and to leverage the power of the TiDB and the TiKV and the TiFlash at the same time. Okay, here's the example that Ed just showed you. So we want to take a little bit deep look at the plan. So there are 3 tables. The largest table is GitHub events. There are 4 billion, more than 4.6 billion rows there. And then we have the database repo table. There are about 46 record there. And then we have the user table. So we are going to find which country or regions, or actually top 10 using this query. Top 10 countries and regions with the database contribution in 2021. So this is the result. We can see the top one is USA, the second one is China, and then Germany, India. So this is the result. And how we get this result? So this is the magic. For TiDB query optimizer, we can choose the plan that can best leverage the power of the TiFlash and TiKV. For example, the plan is like this. The first GitHub events table joins the database table. So this join is pushed down to TiFlash because we have a TiFlash coprocessor. We have an MPP computation node, right? So that means this This is a huge join, but since MPP can do this join in a parallel way, so that's the most efficient way. So we can do the hash join here. We build a hash table of the database repo table, and then we do the hash probe from the event table to the database repo table. And then the result is returned to the TiDB. And at the same time, the user table is joined to the join result of the first table by using the index join, which means each result from the first table join result, and then probe the user table by using the user table index. So that's one of the most efficient query plans. So this just show very, I think, the typical example of the how HTAP can be done with TiDB. Okay, so we talk about how TiDB evolved from the OLTP system to a HTAP system, and how TiDB Optimizer can handle this, how we do the query optimization, we do the costing, and how we can find the right or optimal plan, right? And then I will talk about some tuning practice, because we know that there can always be problem with the online system. Either you got a bad plan or performance is not good. When such things happen, how would you do? So I think with TiDB, okay. So I first, I list some reasons that can cause the bad plan or performance. The first one is that optimizer, as I mentioned, optimizer is really hard. It's not perfect, and it's never perfect, never be perfect. So that means the optimizer can choose the bad plan or suboptimal plan. And then we mentioned the stats. The stats can be out of date, right? So if the stats is not good, how could you expect optimizer to generate a good plan? So that's also another reason. The third one is that for some queries or applications, it's not written well. There's some problem, or it's not optimized. So the query itself can be bad. And then there can be a bad database physical design. For example, the database is lack of some index or partition, schema is not good. All those things can result in a bad plan or bad performance. And of course, there can be some code defect in the database kernel. And there are some also some common DBA approach to impact optimizer to tune the query plan or performance. For example, they can manipulate the stats or collect the new stats, and also they can rewrite the query. They can use the system knobs to tune the system, and also they can use a hint, right? They can use a hint to to tell optimizer what plan you should choose. And I think that most of all, the tooling is very important. So that's why with TiDB, we provide a bunch of tools here. For example, we provide a slow query for user to identify what queries are running slow and what's the troublemaker. And the dashboard is visualize the slow query or top query too for user to find the problem query. And then we have the query optimization hint. SPM is stand for the SQL plan management. That one is used to stabilize query plan. You can bind the query with a certain plan. So just in case if there's something changed, the plan just keep the same. There's no plan regression. So that's also very important. And also we have this plan replayer for users to generate information for optimizer to recreate the problem. So that's also important. And then we can advise user to manually rewrite. Okay, so this is the slow query. So we do have this this field. We call it slow query. You can always select from this slow query view to find how many slow queries are on each TiDB server and what the actual slow query is. So by doing this, you can find the troublemaker. And if you want to drill in more deeper, so you can find the actual plan for each slow query. So that's also very important. Actually, it helps our users and customers to drill down the actual troublemaker and what can be the problem. For example, there are always, for example, the query use the full table scan for a big table, and that will always cause the trouble. So by looking at those information, you can quickly find what's the root cause. And this is a similar one, but it's visualized. We call it a TiDB dashboard. So you can always check the, you can order the, for example, the latency, or order the memory usage to find the troublemaker. And this is for the details you can find out in the TiDB dashboard. And we do have a side of query optimizer for user to impact or influence the query optimizer to choose the right query plan. So that's a very helpful. And I won't go through the detail. And also, as I mentioned, we do have this SPM, SQL plan management, to stabilize the query plan. Okay, next I will talk about some lessons we learned during the past 7 or 8 years journey when we are building this TiDB and the TiDB Optimizer. I won't go through each of this, but I want to point out some. For example, I mentioned that the cost model and the cardinality estimation, right? So here, the cardinality estimation is more important, as I already explained. So that means if you have a good cardinality estimation, very likely you can get a good plan. So that's very important. And the second thing is the stats. That's also the first thing I discussed during the talk. So stats is very, very important to make, you always need to make sure you have the up-to-date stats, and you always have the enough stats for your index, for your columns, for your query. So that's very important. And also yeah, there are some lessons we learned. So when you introduce the new stats, for example, in TiDB 5.0, we introduced the around the 5.0, we introduced a stats called a CM sketch. That one is a good one, especially several papers, academic paper talk about that one, and it's good. But in reality, it can cause problem because why? When the distinct value are huge, there are always a hash collision with this CM sketch. So when you introduce some new stats, so you need to be very, very cautious how it works in reality. So that's lessons we learned. Also the feedback. I think quite several works talk about the feedback to use the execution information to feedback to the optimizer to correct its estimation or correct its decision, right? But that one also need to be very, very careful. We do learn something from that too. And yeah, I think here for the customers, stabilization or stable always comes first before the performance, which means for customer, if they see the performance improved, like for query, it runs like 10 seconds the first day, and then 1 second next day, and then 20 seconds the third day. So that will be a terrible thing for the user, because for the business, they want a predictable performance. Now this unpredictable performance, although sometimes it can run very fast, but for the user, they don't want that. They want a very stable and predictable performance. So that's very important. And also, I mentioned here, for most of users, they probably don't care about 80% of the user, they don't care about whether your plan is optimal or not. They cannot tell, but they want to know their plan is stable. So that's very important. Actually, I won't go through all the lessons we learned. And here are some challenges to overcome, not just by TiDB, but seen by almost all the commercial optimizer, database optimizer face the similar challenge. For example, the stats are very important in how to get a sufficient and accurate stats without impacting the system. That's very important and also very challenging. And also the, especially when it comes to the AP workload, the query optimization can be very, very computation heavy and resources consumption. So it's very important to optimize or mitigate optimization overhead. And also since the system architecture are evolving, for example, at TiDB, we have this storage and computation decoupling, and also even with the storage, we have the row store and the column store, and all those architecture, evolving architecture can put a new challenge to query optimizer. So those are also challenges, and also since we have more and more data and more type of data. Structure, semi-structure, and all those data come in. So application side, they can be more and more complex. That makes the additional challenge to query optimizer to optimize the workload for those new data. Actually, I won't go through everything. But if you are interested, we can talk offline. And next, I will share some work on the on the road. First, we're going to provide a visual plan. So that's important for the user, especially when they look at a very complicated query plan. If you just use the current explain output, the text output, sometimes it's really hard to read. So we'll provide a visual plan, and on top of the visual plan, we'll provide some plan diagnosis for the users and or advisors. So this is important for the cloud users. Why? Because for the traditional database users, for example, for the big company, they do have the DBA team. So they do have this query tuning experience or expertise. But for the cloud users, majority of the cloud users probably don't have such expertise. So that means we need to give them the automatic plan diagnosis and advisories. And also we have some other features on the road. I won't go through each of these, but I think this is about something we're going to deliver soon. And last, since our TiDB has 3 components, TiDB, TiDB, and TiFlash, and you are welcome to contribute. And I think all these components are open source, so you're welcome to contribute. And then last thing is that we provide a TiDB cloud, and then service, you can try it yourself. Okay, I think let's conclude my part.